Hey everybody, I was going to go on a bike ride, but turns out my tire pressure is low because it's really cold today. Oh, there's the pressure recommendation, 50 to 85 psi. Oh, what's a psi? That's a unit of pressure. And why did the pressure go down when it got cold? Well, that's what we're talking about today because we're talking about gas laws. You know, I don't think I'm going to go on a bike ride because I'm too tired. I hate myself. Well, howdy everybody, howdy, Mike here, and we're going to talk about the gas laws today. So when talking about gases, let's go back to the beginning of the course where we talked about the three phases. I want you to visualize gas molecules as being in complete random motion, and they're whacking into the sides of the containers and each other, and that will help us visualize a lot of the factors that we will calculate with gases. And so first of all, variables. I'll go in order of how much you're comfortable with them. You all know what moles are. That's simply number of molecules, right? Or 6.02 times 10 to the 23 molecules is a mole. You know what volume is, right? That's just the three-dimensional space things take up. You know what temperature is. And that is, of course, has to be measured in Kelvin when we deal with gases. So get used to adding 273 to all your temperatures. Do that right off the bat when we're solving these problems. Finally, something I haven't quite talked about yet, and that is pressure. Pressure is what happens when gases hit the side of the container and exert a force per unit area. Now there's a whole bunch more than just 3 molecules in a gas sample. So think of that as the cumulative force of all those collisions with the side of the wall of the container. It's really just physics, right? If you go and throw a golf ball at a fence and it hits, it exerts a force depending on its speed and its mass and all that kind of stuff. So a lot of this gas law stuff is really just kind of boils down to physics. Now, there's the reason we use pressure for gases is because at room conditions, gases are roughly 999 parts out of 1,000 empty space. So you could go and take your car into the garage and say, hey, I think I need air in my tires. And theoretically, you could weigh your tires and find out they don't have enough air in them. But that'd be extremely inconvenient. So it's inconvenient to weigh gases and much more convenient to measure their pressure. So let's talk about the units of pressure and how we use them. There are many different ones. Along the lines of your automobile, when you go and you measure your tire pressure, that's in units of force per unit area, pounds per square inch, or what we call colloquially PSI. We have a unit called atmosphere. That is roughly what the atmospheric pressure is at ground level, sea level I should say, on a dry day. Now keep in mind, the atmospheric pressure that pushes on us depends on our elevation. So here in good old Dayton, Ohio, we're at like 750 feet. And so we have less atmosphere on top of us than someone would be at sea level. Not to mention the amount of moisture in the air. Water vapor makes it heavier or lighter. I don't want to get into that yet. But there was a nifty kind of apparatus called a barometer, which was invented by a guy named Torricelli. And it's really simple. If this was made out of water, this would be 33.5 feet tall, but we usually use mercury. And so the atmospheric pressure pushing down on us forces the mercury up a column, and we just measure that length. So if the air over us got heavier, it would exert more force, and this length would be greater. And mercury is real dense stuff, folks. It's like got a density of like 13.6. So under normal conditions, an atmosphere, if we're at sea level with a dry atmosphere, would be about 14.7 psi's. This would be 760 millimeters of mercury, which is not even a meter. So it's very convenient to use mercury if you don't spill it or breathe it. And now we also have units called kilopascals, which is 101.325 kilopascals. All these, and bars, I didn't have enough room to write bars. Bars were on my tires of my bike, as you saw. And so all these are equal, and you will see them interchangeably, and there's really different uses for each one. But by the way, you know, so if you increase the pressure by a factor of 2, all these units are proportional and they will all double. So let's get to the meat of solving problems with gases. All right, so first of all, let's focus on this. This is called the gas constant. If you take the 4 variables, P, pressure, volume, moles, temperature, if you divide PV, pressure times volume, by number of moles and temperature, you get about the same number. We call this the gas constant. So it's actually funny, and then don't let it play with your mind here. Look, so if you took the number of moles and doubled it, you'd say, hey, didn't that throw it off and make it half? No, what would happen is the pressure would double. So they all kind of counter each other out. And so this constant is pretty darn reliable as long as you're under what we call ideal conditions. What does ideal conditions mean? That means that, you know, if we can basically say that molecules don't interact with each other, meaning that when they bounce off each other, there's no loss of energy. We're going to assume that all of the collisions of molecules with other molecules, they just don't even know they're there. They don't lose any energy when they whack into each other. And that is not perfectly true. Think about something that is polar. Polar molecule hits other polar molecule, they're going to stick. But remember, under room conditions, which are kind of what we call ideal conditions, they're 999 parts out of 1,000 empty space. So there's not many collisions between molecules, and we can kind of ignore that. We can also ignore their volume. Take like everybody who's watching this, we got, say, a bunch of people watching this. We all put blindfolds on and we go wander around in the living room and we, you know, think of ourselves as gas molecules. Well, you know, that living room's pretty small, and we could say, well, what's the volume of the living room is length times width times height. Well, you know, it's pretty small, and our volume is about 60 liters per human being. We'd have to subtract out our volume to figure out the available space. But if we went into a gigantic stadium and did that, you could pretty much ignore our volume. So there's times when the gas constant is very accurate, and that's when you don't crowd molecules and you don't drain the energy out of them. So the gas constant is very reliable at high temperatures, when you're not close to the liquefaction of gases where they stick to each other. Big volumes, which is also low pressure, which we're going to find out, so that there's not many collisions, and then low number of moles, so that there are not many conditions. So what we're going to do next is we're going to use the gas constant to show you where we come up with all these equations that are the gas laws. Let's do that next. All right, now folks, I do want to say in my 27 years of teaching chemistry, I don't like people memorizing surface facts like equations. It turns out that there's also surface facts to the gas laws, like their names. If you're a student in my course, I'll tell you the name of each gas law, but it doesn't really matter. The bottom line is it all stems from the gas constant. So if PV over NT is a constant, and we change some conditions, which is what most gas law problems are, like, hey, we did this to a gas after it was at this point. We could say that these conditions 1 and 2, P1 V1 over N1 T1 equals P2 V2 over N2 T2. We're just saying that there doesn't matter what P, V, and NT are, they're going to be, since they're both equal to the gas constant, we can set them equal to each other. And this is going to be your friend. So you will always see this given. And you could always look at the units. You could say, hey, that's units of pressure, volume, moles, temperature. You can write PV over NT. And you can say, well, P1 V1 equals, P1 V1 divided by N1 T1 is equal to P2 V2 divided by N2 T2. And you can come up with every single gas law there is. The only thing is you'll be missing the name, so if your instructor says memorize the name, well then, you know, that's a bummer. But I don't particularly do that myself. Matter of fact, most of the gas laws are where we have two of these variables constant and the other two are changing. So let's go derive one. And that's powerful, you know, when you have the ability to come up with every single relationship. So this is called Boyle's law. And Boyle's law is where the number of moles and temperature are both constant. So, okay, that means moles are constant, temperature is constant. This thing simplifies. I know the moles and temperature are there. This says P1 V1 equals P2 V2. That will mostly simplify all those problems you get. You could say P times V equals K as well, depending on you know, what you're trying to do, whether you're trying to draw a graph. And that's called Boyle's law, the pressure and volume law. Like if I squeeze on a gas in a cylinder and push on a cylinder and what its pressure will do. This is called Mundsens law, sometimes called Gay-Lusaac's law. If you have a rigid container so that the volume is constant, that doesn't leak so the moles are constant, I can say that the moles are constant just like the last one. And I could say that the volume is constant, so P1 over T1 equals P2 over V2. And you could also say P divided by T is a constant, which means that P equals K times T. If you plotted pressure against temperature, it'd be a linear relationship. But here you go, we just simplified and we came up with a nice little relationship. Avogadro's law is where the number of, where the temperature is constant and the pressure is constant, which means that, okay, the number of moles could change. So P is constant, get rid of the P's, T is constant. That is V1 over N1 equals V2 over N2. Fair enough? And that would be called Avogadro's law. Finally, Charles' law. What happens to a gas if I heat it up and its pressure is constant, like a bubble, right? Like a bubble or a balloon. N is constant because the container isn't leaking or being added to. Pressure is constant. Oh, darn, that was supposed to be this. Sorry, that was me goofing up. And that means that P was constant, and that means V1 over T1 equals V2 over T2. So this is kind of a gas expansion law. Remember, your units in temperature have got to be in Kelvin. Fair enough? Okay, guess what it is? Practice time, whoop! Practice time, whoop, whoop! Now look, we didn't tell you what gas law this is, so let's give it a shot. Okay, and now you're going to read these like a computer. A 750 milliliter sample of a gas. This is, I'm going to call that V1. Exerts a pressure of 46.65 kPa. That's kilopascals. That's pressure. We call it P1. If the pressure, okay, I'll stop doing that stupid voice. If the pressure is changed to 14.95, I'll call it P2. Kilopascals. What's the new volume? V2. The only thing, I know V1, I know P1. So now what you could do is you could start out saying, geez, I don't know what gas law this is. I could say it's P1 V1 over N1 T1 equals P2 V2 over N2 T2. And since they didn't mention the volume, they said it was a, oh sorry, since they didn't mention the moles, they said it was a sample of a gas. Okay, that tells me moles are constant. They didn't mention temperature change. That means temperature was constant. This is Boyle's law, and you don't even have to remember that it's called Boyle's law. P1 V1 is P2 V2. And now what I could do is I could just plug in here. I could say, okay, I got everything. If you like to rearrange first, you could say, well, I'm going to divide both sides by P2. And then I could say V2 is equal to P1 V1 over P2. And I could just plug them all in. Make sure you put them all in the right place. Now, by the way, you can also see what's going to happen here. The pressure went down. So the pressure went down, the volume better have gone up. So this better be a higher volume. You get good at seeing that kind of thing. So V2 is going to be 750 milliliters. And I did it out of order, but who cares? The P1 was 46.65 kilopascals divided by 14.95 kilopascals. Kilopascal units cancel. I get units of milliliters. And like I said, it should get bigger. And if you don't get units of milliliters or volume, then something, folks, has gone quite awry. And so divided by 14.95. Everything is in 3 or 4 digits. I get on my calculator 2,340 milliliters. And actually, since there's a 0 at the end, I could go ahead and leave it there. That's about 3 significant figures. All right, so there you go. And so what happened is if you've pictured this as a piston, you know, if I'm pushing on it and then I pull on it and make the pressure less, the volume would go up. And it did. And if you wanted to, you could plug it back in and make sure you got the same on both sides. You could plug in both P and V's and make sure it's the same. Let's try some more. Whoop. All right, I'll stop with the Mike's bike tire. Hey, remember my bike tires? Huh? I'm going to try to take a bike ride today, though. Have a pressure of 74 psi. Tried to make it realistic. P1. On a warm day, P2 or T1. What would the pressure be on a cold night? Okay, T2. So let's start off here. Let's say, oh, geez, okay, I don't know what gas law it is. P1 V1 over N1 T1 equals P2 V2 over N2 T2. It didn't say anything about moles. It didn't say anything about the volume of a tire, and an inflated tire has roughly, you know, the same volume as it does when it's, you know, partially inflated as when it's completely inflated. This is what we call Mundsens law. It is the tire pressure law on a cold day, or it's the New England Patriots law. Sorry. Now, what we could do is we could, what we have to do, we gotta convert our temperatures. Whenever you see a temperature, go and waste no time in changing it to Kelvin. 3 degrees C, get rid of that, add 273. There's 276 Kelvin. Don't get suckered into doing anything otherwise, because you will massively over or underestimate your result. 295 Kelvin. So if I go ahead and plug everything into the correct place, or if you like to solve it first, what are we solving for? We're solving for P2. So I'm going to go in here and I'm going to multiply both sides by T2. And then, you know, if that's the way you like to do it, cool. That means P2 equals P1 over T1 times T2. And now what you should probably also be able to use your imagination. Now on a cold day, you know, the pressure should go down. And if it doesn't, then we're in trouble, aren't we? So I'm going to go ahead and make sure I put everything in the correct place. 74 psi divided by T1 was 295 Kelvin times T2, 276 Kelvin. And that will be my lower pressure. So let's go see what it is. And you know, when you convert things to Kelvin, you find out that even though the temperature change seems like a lot to us, it ain't on a big old scale. And so this will be 69, now let's see, 69.23 psi, but everything in pressure was in 2 significant figures and said 69 psi. So it went down a little bit. And maybe you've been the victim of this. You ever wake up on a cold morning and then your little tire pressure indicator light is on, and then you're like, I'm just going to ignore that for now. Oh, it went away because the temperature went up Sometimes you get lucky like that. That's Amundsen's law that you just benefited from. Thank whoever Amundsen was, or Gay-Lusaac, those two guys. Hey, one more to go. This one's going to be a little bit tougher. Oh boy, weather balloon problem, huh? Okay, we can handle. Look at all those words. I'm so intimidated. Look at all those numbers. We got this. All right, let's just go through and read it like okay, weather balloon, volume, V1, is launched from the ground where the temperature is T1. I'm going to go change it to kelvins. 273 plus 23. 296 is T1. Pressure is 14.49. That's P1. Okay, we got a P1. Now it goes to 30,000 feet, and you're like, oh, where's 30,000 feet? I haven't done anything with 30. That's just extra information. You just ignore the extra information. It's not really pertinent to this. It's kind of like social media. You just kind of ignore it. It doesn't really belong in your brain. So where's the up at 30,000 feet, though, the pressure is way lower, P2. The temperature is way lower. I looked these numbers up. Negative 44 degrees. We're going to call it T2, but I'm going to get rid of Celsius so you don't get suckered into that. 273 minus 44 is 273 minus 44 is 229. All right, and so now we've got what is the volume of the balloon? V2. We're solving for V2, and so let's go ahead and see how this lays out here. What we got is P1V1 over N1T1 equals P2V2 over N2T2. Okay, what did they say was constant? Pretty much almost nothing, except they said it was a weather balloon and it was a sample of the gas, so the moles don't change. What gas law is that? That is actually called the combined gas law, and that is named after Charles W. Combined. Now, I'm just joking. That's just, I don't know why they call it the combined gas law, but we're going to find out. We need V2. I'm going to solve for V2. Why am I going to do that? I'm going to multiply both sides by T2 and divide both sides by P2. That cancels that. But T2 divided by P2. Remember, now here more importantly, you got a lot of variables going on, right? I'm going to go ahead and write it over again. V2 equals, that should have canceled there. V2 equals T2 over P2 times P1 V1 over T1. Now, you better get units of volume. All right, we better get units of liters. So you keep yourself honest here when you do these things, all right? So I'm going to go ahead and I'm going to plug in all the numbers, and I better get units of volume, and I'm just going to go ahead and do what was laid out here. So T2, what was T2? 229 Kelvin. What was P2? I'm sorry, what was, okay, that was T2. You can cross them out too or something. See, I got all twisted there. What is P2? 4.37 psi. What was P1? P1 was 14.49 psi. What was V1? V1 was 50 liters. And then what was T1? T1 was 23 degrees Celsius way up here, and it's 296. So what's going on? Well, what's going on is I better check myself before I wreck myself and make sure my units all cancel. Kelvins cancel, PSI cancel. And so what I got going on is I got a way lower pressure, but also a way lower temperature. They kind of fight each other, those two terms, and who's going to win? We'll find out. And, you know, weather balloons do expand when they go up there. No, I might have spoiled it, darn. 14.49 times 229 times 50 divided by 4.37 divided by 296. And I got 128.26 liters. And since some things were in 2 digits, like my 23 degrees, I'm going to go ahead and I'm going to call that 130 liters for sig figs. 2 significant figures. Does that make sense? Yeah, you know, like I said, temperature changes aren't that great when you put them in Kelvin. That pressure change was almost like a 3-fold change, and the volume was a little less than 3-fold change bigger. So it kind of makes sense to me. It does not make sense. You could always plug it back in and make sure that P1 V1 over T1 is equal on both sides to check yourself. Okay, folks, that was a lot of number crunching. And get used to it, because next time we're going to talk about the ideal gas law, which also comes from the gas constant. And so keep in mind that all this stuff came from that bad boy, the gas constant. And so does the next thing we're talking about. So just remember, 0.0821, look at the units, PV over NT. Get you through everything. No disrespect to Charles and Edmonton and Avogadro and all those cats, but what's really important is we solve the problem, not do history in this particular outcome. All right, I'm going to get in trouble, so I'm going to sign off. See you later. Ciao.